Hi everyone, welcome to my channel. Haven't thought of a name yet, but I'm sure there will be one once you've watched it. So yeah, whatever the channel name is, welcome to that. My name is Ansar Dolly. I'm a second year student studying actuarial science. Yeah, so this basically is hopefully going to be a YouTube channel where I kind of post educational slash explanatory slash going through work videos for, well, currently just math stats, but who knows where things might go. So I just want to give you a bit of motivation. Obviously, if you've read the WhatsApp message and you kind of know, but like, I might as well just explain it anyway, because I don't know who's going to be watching this. So the first, like, the major motivator is that I want to be able to help people. It's a very, very stressful and interesting time that we live in currently. If you're watching this in the future, like it's kind of COVID-19 pandemic in the middle of that. So like that's what you can imagine. And so I want to be able to help anyone that I can. Secondly, I have had the privilege of having amazing teachers in the past, either through YouTube or in person, or a friend of mine that could just help me answer something. And so I feel that it's time for me to give back. Thirdly, I think that with regards to a lot of university materials, the people that are teaching us are, experts in their field. They've been working through this content for maybe 5, 10, 15 years of their lives, so they are quite used to it. And so when they teach it, it's sometimes difficult for people to kind of remember what it's like to not know something and then have to explain it, rather than just explaining it based on, like how you know it. And then also, like the textbook and the textbooks that we get are quite in depth and they cater to a large range of types of people in terms of like the level of depth that you need to go into something. So I just feel that like I can give a unique perspective on the content because one, it's not my first time like going through this content, but also I haven't gone, I mean, I've only recently done it. I mean, recent being like in the last 3 or 4 years. So, and I've done it multiple times. So yeah, that's why I think I can give a unique perspective on the content. And then, I mean, lastly, this is kind of a selfish reason, but it's also just, it's to consolidate my own understanding of the work. So if I understand it well enough to explain it to someone, then I know that I understand the work. So yeah, that's my motivation. Just a quick disclaimer about these videos and about the channel in general. One, I am not a lecturer. So yeah, excuse me if like I, like ramble on for like 3 minutes or explain something in a weird way. So I'm, yeah, not a lecturer. Don't even have a degree yet. I'm not even completely done with this course. So yeah, obviously I'm explaining things the way I understand them, and if I have misunderstood something or if you think that I've mistakenly explained something, please go ahead, correct me in the comments, or I don't know, send me a message if you have my number. Yeah, I'm open to criticism. Okay, cool. So last point before we actually get onto the work, is just like the format of how I want to go about doing these videos. So the first thing is like, essentially there's like 3 different types of videos I want to be able to do. The first one is concept videos, so essentially explaining things, going through the kind of theory behind what's going on in the content that we're doing. And that's basically just to give you guys perspective and so that you have a second reference about like how to understand things. Obviously, first go through the lecture notes, go through the textbook, and then kind of come here. Alternatively, if I'm your first port of call, I mean, well done to me, I guess. That would be awesome. But yeah, make sure that you do actually, yeah, consult your official learning materials for these talks slash videos. I don't know what to call them at this point in time. The second type of video that I want to be able to do is question or exercise videos. So this is basically going to be very practical. I would go through a specific question, go through all of the, I don't know, key points that you have to remember, go through where a lot of people would probably get confused, things like that. And then the last type of question, the last type of video, which I want to be able to do, it's a bit weird, but it's proof videos. So essentially, these are specific things that either you need to know how to be able to prove, or I kind of just want to show the proof because it's interesting, or it gives you a certain level of an extra level of understanding of the concepts. Okay, so that's the 5-minute introduction. The other thing is I realize this is probably going to be lengthy videos, so it's not going to be like 10-15 minutes. It's probably going to be like 30 to 40 minutes, or like an actual lecture. But yeah, that's just because also this is the introduction. It's the first video, and I'm still figuring everything out. So bear with me. Cool. Let's get on to the first topic. Okay, so the first topic is about statistical inferences and sampling distributions. So it is a kind of explainer / explanatory type of video. So I'm not going to be doing any like going through any practical examples right now. There will be other videos where we start talking about like sampling distributions that are based on the normal distribution, but that will be later videos. So today we're going to be talking about statistical inference. So this is the big picture. And the reason I want to do a big picture, and you'll notice that I justify a lot of my reasons for things a lot. The reason I do that is because I find that one, sometimes people don't know why I'm doing things, or I say me, but sometimes people don't know why lecturers are doing things a certain way, and then that gets them confused in a lecture, and then that kind of makes second confusion on top of like the complexity of the work. So anyway, why am I doing a big picture? I'm doing a big picture because a lot of material that we get taught, we get little to no context about it. So either we're just taught a formula, or we're taught a theorem or a definition, and that's kind of it. And then, you know, it takes us like 3 or 4 years, or like 2 or 3 other courses to figure out, oh, that's why that's important. Yeah, so that's one. Two, also, I feel like, you know, lots of people, myself included, when we get that whole just like years, all of the information all at once, it's very easy to feel lost, to feel like, where is this going? Why am I doing this? You know, like, why are we doing this particular thing? And then ultimately, knowing where you're working towards makes it easier to learn, like, why you're doing certain things. Because if you have an end goal in mind, you can always just kind of reiterate to yourself, this is why I'm doing a particular thing, because my end goal is to ultimately be able to do X, Y, and Z. So that's why this is important. So that's why I need to understand this particular thing. Okay, so let's get into the big picture. So up until this point in our educational career, we've kind of been dealing with a very theoretical understanding of probability and uncertainty or random events. So the kind of basic building block of probability and of random events is something called a random experiment. And every random experiment has something called a probability space, and that has various things. It's not super important that you understand that, but what is important is that one of the results from all of that, you know, theory that you don't really need to know is these things called random variables. Now, random variables are mathematical constructs. And what I mean by mathematical constructs is that we have essentially created the idea of a random variable. A random variable doesn't actually exist in real life. You won't be able to find a random variable if you go and look in the forest or something. There's going to be a random variable lying there. You know, it's not a physical object, it's a mathematical construct. Specifically, a random variable is a function from the all of the possible outcomes of a random experiment to the real number line. Not important. Like, genuinely, it's inconsequential to understand those first, or that line there about a function. What is important though is that random variables have distributions. Now, distributions give us probabilities of outcomes. And we can describe distributions either using a cumulative distribution function, we can describe it using an MGF, we can describe it using a PDF. Yeah, and that's kind of all the stuff that we did in term 1. Now, what's important with distributions is that distributions give us probabilities of outcomes, but what they give us, what the outcomes are, kind of depend on what the random variable is describing. So random variables help model the probabilities of events in a random experiment. And what's super important, what's like kind of a very key idea, is that random variables are models of random phenomena in a perfect world. So what I mean by that is that a random variable isn't going to describe perfectly, exactly a specific type of random phenomena unless the random phenomena lends itself well to being described by a random variable, but that doesn't really happen a lot. Yeah, well, I say happen a lot. I mean, we use it every day, so it must happen a lot, but it doesn't happen perfectly. Essentially, models, they're not a perfect description, but they're good enough to be useful. Now, usefulness is a kind of magical word, a magical word that gets thrown around a lot. Useful obviously has a very specific meaning, well, not specific, but has a different meaning depending on what you're doing. So for instance, we could model the sorry, I'm an actuary, so, well, I'm not an actuary, sorry, that's a mistake, but I'm starting to become an actuary, so my kind of frame of view is quite morbid. But for instance, we can use a random variable to describe or model the amount of car crashes that will happen in a specific city during a particular year. You might model it as a person, whatever. What's important there is that that random variable we are now using as a model, we are using it as a kind of, instead of thinking about the super complex random experiment of how many people crash their cars every single year in a particular city, like instead of thinking about all the possible complex outcomes or scenarios of that random experiment, we kind of simplify and we condense all of that information into one single idea called a random variable. Now, all random variables have parameters, and those parameters are parameters on the distribution, and essentially they are assumptions. They are certain things that we like to think happen, but might not, and we might not know if it does. But essentially those assumptions are the ideas or the beliefs that we have in the particular random experiment that we are trying to model. Now, what's important with parameters is that parameters affect or determine the distribution that you have. If you have a Poisson where lambda is equal to 3, that's going to be different to a Poisson with lambda equal to 17. Those are different distributions. They give you different probabilities. So, random variables give us an idea of what we think we should get or what we expect to see in the real world, and depending on the assumptions we make, whether that be the parameter of a specific distribution or whether it be the actual distribution itself, that will affect, those assumptions that we make will affect what outcomes we expect to see, or those will affect the probabilities. Now, in the real world, we don't have random variables, but we observe outcomes of random variables. So you can think of maybe going to a casino and watching the roulette wheel and looking at what the number on top of the dice or two dices are. I don't really know how roulette works. I'm not a gambler. But you can go out and you can observe that particular random experiment or the outcome of that random experiment. You can also flip a coin a million times and count how many heads or tails you get, and that's observations, because there's a random experiment that happens. It could either be one thing or another. You don't really know, but what's important is, regardless of what you think might happen, you observe a particular outcome. So you observe the outcome of a random variable. What that means is that because you observe the outcome, your theoretical probability on whatever random variable you use to model that particular a random experiment, the theoretical probabilities are not as useful. And I'm saying useful again, useful asterisk depends on what you mean, or depends on the specific circumstance you're in. But essentially you can think about it like this. If there's a random experiment, you have this kind of timeline between what happens before the experiment happens and then what happens after the experiment. So before the experiment, you have a theoretical model of what's going to happen. You have a random variable, you have a distribution, you have probabilities. After the experiment, however, you have an outcome, which means regardless of what happened before the experiment or or how you modeled it, you now have an outcome. And so your probabilities that you kind of created before the outcome happened, before the random experiment was done, it's not that useful to you. But you have outcomes, so you have observations. What can you do with those observations? Well, there's kind of two things you can do. You can either do descriptive statistics, which is what most of term 1 was about. I mean, not what most of term 1 was about, most of the first week of term 1 was about that, all those like frequency diagrams and frequency tables and like, I don't know, sample means, and I know that's descriptive statistics, doing all those graphs and things. The other thing that you can do is make inferences. Now, inferences is the definition according to Google. I don't know if you want to use that, but inferences are conclusions reached on the basis of evidence and reasoning. So I'm going to stop there. Inferences are conclusions reached on the basis of evidence meaning outcomes, and reasoning meaning, well, in this case, reasoning means like a mathematical theory of probability. But that's besides the point. Examples of inferences, I can infer that the mean height or the average height of second year students is 170 centimeters. How I get to that conclusion, how I get to that inference, I can do multiple things. I can go and measure people's heights, which is a very useful way of doing that inference, and a good way of doing that inference. Or another way I can infer that is simply by going into a second year class and just looking at people and being like, I think it's 170. That's a less useful inference and a less, what's the word? I'm going to say good. It's a worse inference than the first one, because you're not really basing it on any other evidence other than your eyes, which can be quite subjective. Anyway, another example of an inference is, for instance, if we look at the average mark of math stat students in 2019 and we compare it to the average mark in 2020, we might say that the average mark of 2020 is greater than the average mark of 2019 based on a sample of maybe 50 students. Why that would happen, I don't know, but that might be the case this year. We don't know. They might actually do that. But the important point about the real world and statistical inference is that once we make inferences, those inferences give us information about our models or our assumptions. So our inferences can give us feedback on what we assume to be true for our theoretical understanding of the random experiment before it happened. And then once it's happened, once the experiment has happened and we've made observations, we've made samples, whatever, we can then look at that data, those observations, and then make inferences, calculate statistics, and determine, okay, our model was a good model, a good assumption, because what we expected to happen actually happened. And that's kind of the big picture of statistical inferences, or statistical inference for term 2. Okay, so how do we go about making inferences? Now, I mentioned earlier that like your inferences can be made in multiple ways. You can, go out and measure things, or you could just kind of guess. But if you want to make good inferences, which are inferences made based on evidence and reasoning, then there's a kind of a specific, I'm going to say, process that you follow. So the first thing is you have to observe data. So you have to go out and take measurements or some kind of objective way of going about looking at something. So there has to be some set of measurements taken essentially, and ultimately what that means is you're going to sample a population. We know what populations are, and usually the population that we're sampling has to do with the model that we are concerned with. So the specific random variable that we're looking at, we need to go about and go and sample that particular population. So for instance, if we want to do the model that I talked about earlier about the car crashes, and like figuring out how many car crashes there are, we need to go and look at, well, what is the data for car crashes? How many car crashes happened last year? How many car crashes happened in a particular other city? You know, that's what sampling is. That's what the observation is about, of getting data. Now, what's important with sampling is that essentially, or what's important about observations is that once you have observed data, you have the outcome of a random experiment or the outcome of a random variable. You don't have the original random variable. It's what I said earlier about, you know, there's kind of a timeline and there's the split in the timeline. Before the experiment, before the random experiment, you have beliefs and you have a distribution, you have a random variable. And then after the experiment, once you've made an observation, once you've seen something, once you've observed data, you have the outcome. So you don't have the random variable. You can still work with the random variable, like you can still go and figure out, well, what was the probability of getting a particular outcome, but it's less important because now you have the outcome. Probabilities are only useful in terms of, oh, no, I won't get into that. Anyway, so all this means is just that studying the original random variable is no longer as useful. So I'll give you an example of what I mean. So there's kind of two different cases. There's the discrete case and the continuous case. We'll start with the discrete case. So imagine Jack and Rose, no reference to the Titanic, no, none whatsoever. They have copyright or whatever, I don't know. Anyway, Jack and Rose both roll a die 12 times. They're separate dice and they count the number of sixes. So, we know we've taken probability, prop stats 1, 2, 4, 1, 1, 4. We know what this kind of random variable can be modeled as. We assume that the xj is Jack's dice and xr is Rose's dice, and they are distributed according to a binomial 12 and 1/6 distribution. So then that's kind of our beliefs about the system or the random experiment before the system or the random experiment has happened. Then the random experiment happens, and afterwards we observe the following. Oh, shit. Okay, I can't go back. Anyway, we observe that Jack's die is equal to 2 and Rose's die is equal to 10. So Jack got 2 12s. Jack got 2 6s and Rose got 10 6s when they rolled each of their separate dice 12 times. So we can go and we can calculate the probability of a particular value happening. So the probability of Jack's dice being equal to 2 is 0.296. And the probability of Rose's die equaling 10 is 7.8 times 10 to the negative 7, which is a very small number. It's super small. You might even say it's almost 0. It's not going to happen. Like you won't have 10. You won't roll 6 10s if you roll a dice 12 times based on that distribution. But regardless of probabilities, regardless of what those probabilities calculated were, we get those outcomes. And this is the important point I'm trying to raise, is that in probability and, like random variable theoretical land, you have beliefs, you have models, you have random variables, but once the random experiment is done, once you've completed the experiment, you have observations. And those observations, while they do have probabilities associated with it, it doesn't matter what not necessarily doesn't matter, but it's less important because regardless of the probabilities, both outcomes have happened. You can think of a continuous case where you measure the heights of 3 of your classmates, and before you do the measurement, you go and do some research about, like height distribution and stuff like that, and you conclude the following, that all three of those random variables, the heights of each one of those friends, are what's important here, and I haven't put it in that little tilde sign thing, but they're identically independent and identically distributed. You'll see that written as IID. It's important. A lot of statistics is based on IID variables or random variables. It doesn't really matter right now. Essentially, it's just that that's the distribution we assume that those heights have, that they have a mean of 165, and that's meant to be 7 squared because the standard deviation of male's height is 7 centimeters roughly. So the variance is 7 squared. So, you know, you go and that's your model, that's your random variable, that's your theoretical model of what you expect to, or kind of what you expect to see essentially in those heights. But then here's the important part. So we've got before the random experiment and now after the random experiment. You observe the following heights. So x1 is 173, x2 is 162, and x3 is 202. Now, if you remember anything about continuous probabilities or continuous random variables, you'll know that the probability of any exact value is equal to 0. So that's kind of like not really what we want. And you can work around it using intervals. So like you can say, what's the probability of being near 173 centimeters, where near means like, you know, plus or minus 0.2 or plus or minus 0.3. You can do that, but regardless of those probabilities, regardless of what the probability is of getting a particular value, those are the outcomes you got. And so what's important is the original random variables that we have, the xj, the xr, x1, x2, x3, those random variables are not useful in the sense of telling us what we can expect, because we don't have any more expectations because we have outcomes. So essentially the expectations and the outcomes, and by expectations I mean probabilities of seeing a particular value, those are less useful. And I've stressed it a lot now, but essentially all that means is that we're not necessarily going to be all that concerned with any one particular random variable's distribution or any one particular random variable's probability of being in a particular interval or being equal to something if it's discrete. So how do we go about making the inferences? So once we have the sample of the data, we have basically sample of the data just means you have observations, you have data, you've gone out and sampled something. You can now make inferences because you have data. You can now do some analysis and you can make a conclusion about the specific data that you have. What is important though is statistics. So statistics, or a statistic, is simply a function of the observable random variables in a sample, i.e. the observations, and known constants and parameters. What this means, basically, because that's the definition out of the textbook, is that a statistic is a way of summarizing a lot of data into like one or two, most of the time it's just one number. And so that statistic that we have is based on our observations, which is important because otherwise what else would we base it on? But the important part, and these are just examples of statistics, the sample mean and the sample variance, the important part is that statistics are random. Or yeah, they're random in the sense that they are based on the sample that we got, that we specifically went out and measured or got data on, and that particular sample that we have is completely random. I could have gone out and measured the top, for instance, if I was measuring heights, and I'll use like specific examples, trivial examples, just to kind of get the idea across. But if I go and measure heights, I could take a random sample of 10 people, and I could, in theory, take the 10 tallest people or the 10 shortest people and calculate a sample mean, and I would get two different values basically. So that sample mean, or that statistic, and I say sample mean here, but any statistic in general, is going to be a random, and it's going to be a random variable. And the reason for that is because any function of a random variable, i.e. the sample mean, the sample variance, other sample things, is a random variable itself. Now, I kind of just want to like highlight something with the sample mean and the sample variance, which is not super important, but it's just sometimes it's weird because, not weird, but sometimes you'll see things written with capital letters and sometimes you'll see things written with small letters, and like, what is the difference? If something's a capital letter, you think of it as being a random variable, as something that could take on a range of values. And if something's a small letter, you think of it being an observation. It's a number that you know. So your sample mean here, you know what xi is because you've gone out and taken those measurements, or those you've gone out and observed those data values, the outcomes basically. But the sample mean, xn bar, whatever you want to call it, it is actually called xn bar. I shouldn't say whatever you want to call it. It's called xn bar. That sample mean is a random variable because that can take on a range of values depending on what the particular sample that you got looked like. So it's not super important to know like the difference between capital versus small letters, but it's just a little point that I want to point out. But getting back to the point of statistics are random variables, because statistics are random variables, they have all the same features as random variables. So they have cumulative distribution functions, they have PDFs sometimes, they have MGFs, moment generating functions, characteristic functions if you want to be super whatever. But essentially what that means is that all of the knowledge that we have about random variables can now be used or applied when we look at statistics, because statistics are themselves random variables. So what I mean by statistics or random variables is that a random variable will have a probability distribution. The distribution describes what the probability of seeing certain values are. So because random statistics are random variables, they have probability distributions. These are called sampling distributions. So what's important about this is that sampling distributions tell you what the probability of seeing a particular statistic value is, or what the probability of seeing a particular not sample, but a statistic of a sample, what the probability of that particular statistic equaling a value is, or being between a certain value is, depending on if it's continuous or discrete. So probability distributions, we kind of know them as either CDFs or PDFs, but this is just the CDF of a particular probability distribution. So what that's saying is that the probability of my sample mean being less than a particular value is f of that value, and f there is then the cumulative distribution function. And cumulative distribution functions, PDFs, MGFs, all of those things, they exist for random variables. CDFs always exist, PDFs not necessarily, MGFs not necessarily, but CDFs always exist. So that's kind of why I'm using a CDF. And a CDF will describe the random variables distribution. So if you can find the distribution of a sample or of a statistic, that's called a sampling distribution. Now, the idea behind statistical inference is that that particular sampling distribution of that particular statistic depends on the distributions of the random variable for which it is a statistic. What I mean by that is that if, for instance, I have 4 or n uniform random variables from 0 to 1, that gives me information, or that gives me an idea as to what the sampling distribution for xn bar is going to be. So for instance, the maximum value that any of those xn's or xi's can take on is 1, right? So then when I add them all up, the maximum value they can be is n, right? And then if I divide by n, because that's what you do during a sample mean, you are going to get 1. So you know, therefore, that the maximum value that xn bar can take on is 1. So for instance, if I ask what's the probability of xn bar being greater than 2, well, based on the information I have, that's 100%. Or no, I lie. That's 0. Because, sorry, that's 0 because the maximum value that my particular random variable can be is 1, based on this information of being uniform and whatever. the maximum value that the sample distribution can be is 1. So basically, by knowing or by using the assumptions we have on the original random variables, right, that we have observations for, using those random variables, we can work out what the sampling distribution or what the probability distribution of a particular statistic is. And so finally, and this is where kind of statistical inference, it's the ultimate goal of statistical inference, is that by using the sampling distribution, by using what the probabilities of seeing a particular statistic fall between, if that makes sense, by using that, we can make inferences, or we can make conclusions about how we modeled our original random variable or our original random experiment. So we can check, well, is a particular parameter value a good parameter value to use? Is a particular distribution a good distribution to use? Is the assumption that they're independent a good assumption? All of those kinds of things are inferences that we can make based on the sampling distribution, because the sampling distribution is determined by what the original random variables are, and those original random variables that we have, we kind of made assumptions about those. So using statistical inference, we can then go and say, okay, our assumptions were good, our assumptions were bad, or this is something we can be super confident in, or this is something we're not super confident in, basically. So that's essentially the kind of end goal of statistical inference, is making conclusions about our assumptions, about our models, about our parameters. Okay, so in the Jack and Rose dye experiment, we assumed that xj and xr were both distributed according to this binomial distribution 12-1-6. Now, the reason we chose that is because we didn't have any other information to tell us anything otherwise. We didn't know that Jack's dice and Rose dice were made maybe in 2 separate factories by 2 separate people. We just knew that there were 2 dice and they were going to roll it 12 times, and based on those 2 pieces of information alone, we kind of just assumed, okay, binomial 12-1-6, right? Now, our observation, or our statistic, in this case, a statistic is a function of the random variable. It's just the random variable, basically the outcome of the random variable. So our statistic is just the value that we get for a particular random variable. So we're not like using a sample mean or sample variance, just a very basic example. Our statistic for Jack's die of being equal to 2, so the fact that we got 2 kind of lines up / agrees with our assumption, since the probability is 0.296. So what I mean by lines up or agrees is that, sorry, we don't really consider that out of the ordinary. Getting a 30% probability for something is not something that's never going to happen. It might happen, and actually it might happen quite a bit, or fairly often with 30% probability. However, for Rose's die, the fact that her die, that she rolled 10 sixes, that doesn't line up with our idea that, or it doesn't line up with our assumption that it's a binomial 12-1-6 distribution, because that probability of 7.58, or the probability of seeing that particular statistic equal to that value, is a very, very small number. Now, throughout most of statistical inferences, you're going to be dealing with this idea of what level of low are we okay with, you know? Like, if something happens 1% of the time, are we going to say that it would never happen? If something happens 0.001% of the time, are we going to say it's never going to happen? And that's kind of where, you know, like specific domain knowledge comes in. Like, what are you trying to model? Is it important that you be very accurate? Those kinds of things. But essentially, just based on this kind of trivial example, we can see that getting 10 sixes is not a likely outcome. It's not going to happen that often. So the fact that it happened for us is weird in a sense. So that weirdness, or that very low likelihood of it happening, is evidence, or it's giving us a reason to maybe conclude that the die that we originally thought were identical are probably not identical, and maybe Rose's die is loaded. Who knows? We would have to do more more analysis, maybe roll it a couple more times, do more things to like be more confident in that conclusion. But ultimately, the conclusion that they're not identically distributed seems pretty like most of us would say, okay, cool, I agree with that conclusion. So that's what statistical inference is all about. That's just the trivial example. So making inferences, there's different ways we can go about making inferences, and there are different types of inferences we can do. So obviously sampling distributions. Come on, Ansar. But sampling distributions are the heart of all of inferential statistics. It's the heart of all the inferential statistics that we do, basically. So this is just like a basic outline of some of the different types of inferential statistics you can do. So confidence intervals are basically all about estimating a parameter by giving it an interval and saying that we are a certain level of confidence, or a certain level of confident, I don't know the correct English description of what I want to say, but essentially confidence interval is saying this is an interval for a particular parameter or a particular value, and we are 95% confident that that value lies there, right? That's what confidence interval is. Or saying that 95%, or we are 95% confident that a particular value will always lie below a certain value or above a certain value. That's what confidence intervals are. Hypothesis testing is a very, very big, broad topic. And it's basically hypotheses are basically just any kind of assumption you can make, and then testing whether that assumption is true based on a certain level of, once again, I will say confidence, or based on a certain level of, I'm going to go with accepted error. We'll obviously get into it later. Hopefully I'll be around for that, and hopefully you will be around there as well. ANOVA stands for analysis of variance, and basically that is the ability to determine whether certain data comes from the same population. So for instance, at the beginning of the video, I spoke about, looking at the average value of MathStats 214 in 2019 and looking at the average MathStats 214 mark in 2020 and seeing, hey, does this data come from the same distribution? Are these marks distributed in the same way? And that's what analysis of variance is all about. And then regression is kind of the heart of machine learning, and that's all about figuring out how much one independent variable can predict a dependent variable and what the kind of error rate is. ANOVA and regression, I think we do regression in MathStats in second semester. ANOVA is a third year level thing, so you don't have to worry about that, and regression you don't have to worry about right now. Mainly, we're going to be working with confidence intervals and hypothesis testing, but what's important is that all of these concepts or tools that we can use rely on sampling distributions. Now, because of that, we need to talk about sampling distributions and how we go about finding sampling distributions. So you can do it in like three multiple ways. You can do it if it's an explicit finite discrete case, and what I mean by that is explicit meaning you want to give the probability of seeing a statistic equal to a certain value for every single value that the statistic can achieve, and you want to give the exact probability, and there are finitely many cases, and all of the cases are discrete. If you have that particular case, then you can do it, but it's tedious. So essentially what you have to do is you have to find all of the possible outcomes of the statistic, and then you have to find the probability of getting that outcome of the statistic by finding the probabilities of the random variable outcomes which lead to a specific outcome of the statistic, and that's kind of what chapter 7.1 does in the first example. And then you cry because it's just annoying. It's very annoying. Alternatively, you can use relationships between the original random variables that you have or that you are modeling and the tools you learned in chapter 6 with functions of variables to find the distribution of your specific statistic, because a statistic is just a function of a random variable. So basically, if you know what the distribution is of the original random variables and you use some, methods that you learned in chapter 6, you can get the distribution of sampling distributions or sampling distributions of specific statistics. That works very well if you have a normally distributed data, because the normal distribution is super nice. And then if you don't have normally distributed data, or doing chapter 6 methods is a bit either tedious or doesn't really yield useful results, then if you have enough data, you can make approximations using CLT, which is called the central limit theorem, and that's kind of another chapter in another sub-chapter in chapter 7, which I will hopefully have a video for. Okay, so that's the end of this video. I know it's quite long, but hopefully this gives you a broad outline of what's happening in term 2. Yeah, and if you like the video, hit like. If you want to see more, please hit subscribe. If you have any questions, obviously put them down in the comments, and then yeah, hopefully I'll see you in the next video. The next video we'll be doing is about sampling distributions of normally distributed data. Cool. Bye.